The fifth example for implicit differentiation involves a combination of rules. Learn about them here in differential calculus. Functions can be written in different variations. One type is explicit, which means a function y is defined in terms of x, like y as equal to negative x cubed multiplied by the binomial 3x raised to 4 minus 2. The second type is implicit, where it is the total opposite of the first. Both sides of the equation contain combinations of variables. Applying these two functions in real-life situations, you might notice that implicit functions are more common. With different variables placed together, the differentiation process in implicit functions need not be exclusive. For two variables, differentiation can be taken as dy over dx, or the other way around, the derivative of x with respect to y. The function for this differentiation is x squared as equal to the square of the binomial 4x squared y cubed plus 1. The first part is to look for y prime, which is also called dy over dx. Similar with the previous example, the square would indicate that the right end is a single term. So we then proceed with the first differentiation, where the derivative of x squared is 2x, with dx over dx. On the right starts with the coefficient 2 times the binomial 4x squared y cubed plus 1 raised to 2 minus 1. Then attach the derivative of the binomial, as required in the chain rule. Dx over dx on the left is taken as 1, and we needed to distribute the derivatives among the terms in the latter binomial. So the function becomes 2x as equal to twice of the original binomial multiplied by the derivative of the first term, 4x squared y cubed, then also the derivative of the second term, 1. The last term is differentiated as 0, and we also move the constant 4 of the derivative up front. The function is then 2x as equal to 2 times the quantity of 4x squared y cubed plus 1 multiplied by the constant 4 with the derivative of x squared y cubed. Taking the others as they are, focus on the last term, which requires the product rule. We then get 2x as equal to twice of the binomial times a factor 4 with the expanded differentiation of x squared times d over dx of y cubed, plus the second term y cubed multiplied by the derivative of x squared. After this expansion, the function became longer, but the terms to be differentiated became simpler. So we further differentiate and have 2x as equal to 2 times the binomial, with 4 times of x squared with the derivative of y cubed, which is 3y squared with dy over dx. Also distribute 4 to the other term and have with it y cubed with 2x, which is the derivative of x squared. Then attach dx upon dx, which eventually cancels out. We can also simplify dy over dx as y prime, which then gives a single-liner function with 2x as equal to twice of 4x squared y cubed plus 1 multiplied by the binomial 12x squared y prime plus 8xy cubed. We then attempt to take the quantities with y prime, So we divide the function by 4x squared y cubed plus 1, and then also cancel the constants 2 from both ends of the equation. The outcome after the division is 12x squared y prime plus 8x y squared as equal to x upon 4x squared y cubed plus 1. Transpose the other term to the right to completely isolate the term with y prime, and have 12x squared y prime as equal to x over 4x squared y cubed plus 1 minus 8x y cubed. To have the prime, we again divide the whole thing by 12x squared y squared, providing more terms in the function, especially those in the denominator. However, it is noticed that there are parts which can cancel out with another. So y prime is then the reciprocal of 12x y squared times the binomial 4x squared y cubed plus 1 minus the fraction 2y over 3x. Since we wish to have a single fraction for our final answer, we take the least common denominator, which is still 12x y squared times the binomial 4x squared y cubed plus 1. The numerator will then be transformed into 1 minus 2y times 4y squared times the binomial 4x squared y cubed plus 1. Although there is limited we can do, let's combine 2y and 4y squared. So the final derivative y prime is then the fraction of 1 minus 8y cubed times 4x squared y cubed plus 1 all over 12xy squared times the quantity of 4x squared y cubed plus 1. This time, we take the other derivative of the function, using dx over dy. But just the same, the start is to understand that the right term is taken as just 1 due to the exponent 2. So instead of distribution, we differentiate. The left side becomes 2x with dx over dx. At the right, we have 2 times the original binomial with the derivative of the same binomial. Distribute d over dx on the terms in the binomial to get 2x dx upon dy as equal to twice of 4x squared y cubed plus 1 with the derivative of 4x squared y cubed, and also the derivative of 1. The last term ends as 0. Then we move the constant before the derivative. So the outcome is 2x dx over dy as equal to twice of the original binomial with 4 times the derivative of x squared y cubed. The next step to take out the derivative is to employ the product rule. So the rest of the function is copied from 2x dx over dy to twice of the binomial 4x squared y cubed plus 1. With the product rule, the expansion then becomes 4 times the first term x squared times the derivative of y cubed plus y cubed with the derivative of x squared. With the expansion completed, we differentiate. So the function then is 2x times dx over dy as equal to twice of the binomial of 4x squared y cubed plus 1. The exterior factor in the derivative is then distributed among the terms to have 4x squared times the derivative of y cubed, making 3y squared with dy over dy. The other term also has 4 times y cubed with the derivative of x squared, which is 2x times dx over dy. Dy over dy is then cancelled out to have 2x times dx over dy as equal to twice of the binomial times another binomial with 12x squared y squared plus 8xy cubed times dx over dy. Since everything has already been simplified, all we needed to do is simple algebra to come up with dx over dy explicitly. We first take out the groupings by performing FOIL method. The left term remains as x with dx over dy, and the right then multiplies the terms to have 48x raised to 4 y raised to 5 when we multiply 4x squared y cubed with 12x squared y squared. Next is 4x squared y cubed times 8xy cubed with dx over dy, resulting to 32x cubed y raised to 6 times dx over dy. The third term is 1 times 12x squared y squared, and that is the same 12x squared y squared. The fourth is also 1 times 8xy cubed, which is the same as 8xy cubed with dx over dy. Without any restrictions, take all terms with dx over dy in one side, where the terms are x, 32x cubed y raised to 6, and 8xy cubed. And they are equated with 48x raised to 4 y raised to 5 plus 12x squared y squared. Factor out x and the derivatives from the three terms to make x times the trinomial of 1 minus 32x squared y raised to 6 minus 8y cubed multiplied by dx over dy as equal to the remaining terms factoring out 12x squared y squared with the binomial 4x squared y cubed plus 1. Take dx over dy by dividing everything by the derivative's coefficient, which then concludes our solution with dx over dy as 12xy squared with the binomial 4x squared y cubed plus 1 all upon the trinomial 1 minus 32x squared y raised to 6 minus 8y cubed.